Greetings. Graham Warren working with you on the AnyLogic model for Neighbor's Coffee Shop. So in this clip, I think we're going to walk through the layout of the AnyLogic model, and then maybe we'll just verify that it roughly chimes with what we saw in the queuing model analysis for that one menu where we have only seasonal lattes. All right, so in broad, we've got the controls here on the left-hand side, and we've got a dashboard that shows you KPIs and graphs and whatnot. The underlying model is down the bottom here. I've got a source block that's generating arrivals at this arrival right here. It's a Poisson stream, which is realistic for sort of a retail establishment, let's say in relatively normal operating hours. Then there's three resource pools we need to talk about. They're sitting down here. There's sales staff. There's currently nobody in that pool. That's why there's a 0 down here and up here. So you can control how many salespeople there are. They're dedicated to taking orders and nothing else. Then we've got spiders. These are dual purpose people who can either take orders or make beverages or anything else they may do, production wise. And then we've got baristas who only do beverage prep. So the spider terminology is sort of borrowed from lean systems thinking, where we've got the water spider idea. So they're just dual purpose. So once you've grabbed a salesperson or a spider, there's options there. So if there are no sales folks available and there are spiders available, then a spider will be grabbed and will serve the customer. We then have order capture. So the three possibilities here. If it's an online order, the time is 0, and then the person is immediately released. So it's essentially as if there was no salesperson or spider involvement. If it is an in-person order, then there are two types of customers. New customers who have an order time of 5 minutes, which seems fairly ridiculous, but I did get that information earlier in the year from Spencer Track, who is the owner. I would argue that it's less, but certainly they do engage and they explain options and so forth. Whether it takes 5 minutes, I doubt. But in any case, there is the new customer with a default order time of 300 seconds. And then there's the returning customer who's seen who's heard the shtick before and is only going to take half that, 150 seconds. It is a fairly elaborate menu. It is an evolving menu. There are a lot of options. So sometime, a minute or two is not unrealistic. This is from the time where you've reached, the head of the line, and you're basically engaging with the person behind the POS, point of sale system. All right, so we've got the order. We release either the salesperson or the spider associated with the ordering process. And the order progresses and lines up for a barista once a barista is available, or failing that, if there's a spider available, then a spider would step in as well. And then there's this labor delay. This is information that comes from table 2 and 3. We're not able to change those process times. But so they're given, but we can change the probability that a customer orders a particular drink. So we're going to call the changing of the probabilities menu engineering. Right, I've got a limited amount of bandwidth here because we're on a free account, so I just have to restart this thing. This is a cloud version. See if I can actually restart this. Might have to get out and refresh it. Yeah. You only get so much compute. All right, so I'll just pause it. So once we've got this labor delay, that's the information from tables 2 and 3. For every drink, there's a specified mean and standard deviation. I think we're assuming normal distributions across the board. And then we release the barista or spider, as the case may be. Then there's the non-labor delay, which is variable. And then the customer, the order exits, the beverage is delivered. All right, so the controls on the game, you've got run the simulation, stop, and then you can decelerate or accelerate. This tells you, what speed you're running at relative to, real time. And then we can also use virtual time, for fast forward to the end. And there is a limit to, how long this thing will run. All right, so the controls, you can control the arrival rate. In the base case, we've got 40 per hour. You can control the probability of an online order. And let's change that to 1 right now. I just have a small start here, so that's going to wash out. We can really estimate, that case, the case that we had for in the queuing model. Recall at 100% seasonal latte setup with 6 baristas. So we're going to try and mimic that here. I have 5 baristas and a water spider, or rather a spider. So that's 6. So I think I'm good on the count. And then I'm going to, what you have here, all the default probabilities in table 2 and 3 in the case. I'm going to hit this button here. This is my best effort to sort of like just clean the slate. I think I actually have to run it, pause it, and maybe I can zero it now. Yeah, there it's zeroed. There is a 1 here because I do want some of the probabilities to be 1 at all times. And so I'm going to just zero that 1 out now and plug 1 in here. Let's try that again. Okay, so that looks like the setup that we have in the queuing model. So I think we had an estimate of, let's see, 5.604 minutes when we did the queuing analysis for this scenario. I'm going to run it now, but let's just, as a verification, I want to just go through the controls with you. So you can change the arrival rate here, the probability of an online order, the probability of a new customer if it is an in-person order. Then there's the order times for new and returning customers, the number of point of sale systems you have. You definitely want to make sure that the point of sale systems is equal to the number of sales staff, or maybe sales staff and spiders, because if you don't have the POS systems, then the sales staff and the spiders could potentially be lining up to actually use one of those collection stations, order collection stations. All right, so then you also could control the number of baristas, sales staff, and spiders. And then, you're doing a menu engineering here. You can verify that your probabilities sum to 1. Maybe full screen that. You can verify the sum to 1 here. Should have enlarged that the first time, I guess, but hopefully we're still good here. Okay, so when the system starts, it's going to start with the default probabilities. And again, you could hit 0 probs to get that set up where you have a 1 for the drip coffee and 0s elsewhere. So it's unfortunately quite laborious to enter these probabilities, for an elaborate menu every time, but it is what it is. Right, so on the output side, or the KPI side, you're going to get, you can see the sort of the impressive graph is this one here, which shows you how many drinks of each type have been made. So you're currently at 4 drip coffees here, 1 matcha, and this is just the legend for this graph up here. Beyond that, you've got 2 histograms down here. This is the flow time from time of arrival to completion of service, beverage in hand. So that's the one we're going to see if it matches up with the 5 point, whatever it was, I think 5.6 something. There's also a separate histogram that's just going to look at the weight from the time of arrival to order collection. Because okay, got the problem again, but let's see if I can redo this. Stop it there. Okay, we'll zero them out again and just set up our no in-person orders. 0 here, 1 here. Maybe it's a good time to just run this to completion now. And you can see it's running all speeded up. See the graphs evolving here. 6 baristas, seasonal lattes only. You can verify the probabilities are good. And I'm going to run it all the way to completion here. So you're going to have 6,687 or so customers hit this thing. And you can see I'm at about 5.68 minutes, which is very close to the queuing analysis. Queuing analysis is an approximation because you're using Kingman's formula, which is exact only for heavy traffic, and I don't think we're in heavy traffic. But let's have a look and see what we've got with this setup for the seasonal only. We don't have any staff people, so sales staff people, so of course 0% utilization. Spider, just one of them, very low utilization, and the baristas are 54.74, 55% utilized. So there are probably too many of them. And the spider is probably spurious. So what I'd probably do is cut one barista here. The baristas are the go-to for the go-to resource pool for making the beverages. The spider is a backup in both cases, for the order collection and for the beverage production. All right, so the average time wait to place an order less than a minute, not too bad. And then the flow time is 5.7 minutes. That's from receipt to exit, and a lot of that is actually going to be production time because these seasonal lattes, you can look it up in the tables, but they take quite a while to actually produce. So there's currently, at the end of the simulation, this is a real-time number, no people at the point of sale terminal, nobody at the beverage station, and the system clock is at 10,000. So you can monitor that as you go. That's the setup. Seems to verify nicely for that one particular use case. And if you do discover little discrepancies, please shout. You can see that it is only, it made all of those 6,680. There were actually 4 more. It must be one of the other types. It's probably a tiny bar here somewhere that isn't hardly even showing up for the other. Well, actually only 6,685 drinks completed. There are 2 stuck still in the labor delay. So yeah, so this is 6,683. I don't know what happened to the other 2 drinks, but it's roughly, there's one matcha. There's one drip. There you go. But not enough to show up in the graph. Cool. All right, so in the next clip, we'll look at maybe one other scenario, just in looking at the default and then sort of reasoning about how you could think about assessing staffing levels for different menus.